Hello everyone, welcome to your lesson on current potential different graphs. So I hope you're all well and you're staying safe from the storm. Before you watch this video, you should have finished off your graphs that we started last lesson. So last lesson we did a practical and then you were plotting the graphs from that. Now I did ask you that if you hadn't drawn the line of best fit on those graphs, then please don't until you've watched this video. So I will talk through what the lines should look like. So the aim of this video is that we are going to be writing notes on why the graphs look like they do, and you will learn the general shapes of them as well. Once you've watched this video, you're going to be doing a worksheet, and again I've got a separate video which is the answers to that worksheet. I prefer videos because you can pause them basically and do things at your own pace as opposed to Zoom whilst you're waiting for everyone else. I don't think it's the most effective use of time. So yes, let's go on. So if you can please title and date for me, potential difference, current graphs. It is the 18th of Feb today, so that is your date. Now our first graph should look like this. This is our resistor. Now I am calling it now an ohmic resistor. What that means is that it follows Ohm's law. Now, if you remember, we did Ohm's law. That was the equation that was made by Georges Simon Ohm. It was V equals IR. Voltage, or potential difference, equals current times resistance. And so an ohmic resistor basically follows the idea that voltage and current are proportional and that resistance stays the same. So what we are seeing in a graph for your resistor is a nice straight line, direct proportional line. Now have a look, that line goes straight from the negative part of the axis through the origin, which is the 0 point, and out the other side into your positive. So as I'm increasing voltage, I'm increasing current. And to the left of this slide, you can see I've explained why that happens. With a higher potential difference, the electrons are given more energy. This means they travel faster and more electrons pass a point per second, i.e. there is a higher current. So when I increase the voltage, I'm increasing the energy, so the electrons move faster, and that's a higher current. So if you have not done the line of best fit for your resistor graph, can you please do that nice straight line? Then can you please copy down those couple of sentences? Now where you copy these down is a choice up to you. You could write those two sentences on your graph so that it explains them. If you don't want to do that and instead you want to write them in your book, can I please ask that you sketch this graph to go alongside it so it makes sense, so you can actually see the graph that you are describing. So pause the video here and copy those down wherever you prefer. Okay, assuming everyone's done that, I'm now going to show you a little animation explaining again why that graph is the way it is. So here we have a circuit and there is one 1.5 volt cell and you can see the electrons going round. Now if I increase the cells to 2, you can see the electrons go faster. Let's increase it again to 4.5 and again the electrons go faster. So there I'm increasing voltage and the current then increases as a result. Now our next graph that we are looking at is a current voltage graph for a bulb. And the reason I was getting you to not draw your lines of best fit before watching this video is because a bulb is a slightly odd shape. It's almost a bit like an S shape. Yours might have a slightly shorter bit in the middle and a slightly bigger curved bit at the top, that's fine, but you're looking for that slightly bent S shape. Now let's describe what we can see. Again, I'm increasing the voltage, which increases the current. But towards the end, you can see that when I increase the voltage, the current does not increase that much. Now, the reason this is happening is basically the current's getting towards the maximum. It can't go any faster. The reason it can't go any faster is actually that bulbs get hot. Do you remember every time we do a practical, I'm always saying, oh, health and safety, remember, bulbs get hot, so be careful. This is an example of what happens as a result of that. When the bulb gets hot, the resistance increases. It's harder for the electrons to get through. So as I increase the voltage, great, I increase the current, but then the bulb starts heating up and current can't get any faster because that resistance has increased. So, yes, increase voltage, increase current, but the bulb heats up, resistance increases. So here's our explanation for that. Let's read it through. As the potential difference increases, the current increases. The fast-moving electrons collide with the positive ions in the wire, transferring kinetic energy. So just pausing. In chemistry, I'm sure you've done metallic bonding, and the idea that in a metal, you have lots of positive metal ions, and then you have a sea of free electrons. It's like those electrons which form the current. So they are the things that are moving. And in a bulb, when they start moving, they start colliding with the ions and giving those ions a bit of kinetic or movement energy. Right, carrying on. The ions start vibrating, the wire gets hot, and they get in the way of the electrons flowing through. Therefore, resistance increases. So, again, can you please draw me a line of best fit on your bulb graph, and hopefully it looks similar to that. And then again, you can either write these sentences on the graph, or you can write them in your book and just sketch the shape of this graph for me. So pause the video here and do that. Okay, next bit. Ooh. Again, I'm showing you a little animation as to why increasing the voltage and increasing the current in a bulb actually causes the electrons to slow down. On this diagram here, you can see a grid of ions. These are the positive ions that are in the metal. This is like the wire. And in a second, we're going to see that sea of free electrons flowing through. So here we go, here's the electrons. Now I'm going to increase the voltage and I'm going to get them to go a bit faster. Nice. But can you see that the ions are starting to vibrate? You can see they're being given a little bit of energy and they're starting to vibrate. And when they do that, basically they get in the way of the electrons. And the more they vibrate, the more they get in the way. So, an analogy, if you're not sure about why that is the case, I want you to imagine you playing, you're at a party and everyone's playing musical statues. And you are trying to carry a tray of drinks through the party. And when everyone is playing the statues part and they're all very, very still, you can duck and dive and you can get around them and it's okay and you can get through fairly quickly. That's like a cool wire. When it is the music and everyone's dancing and you're still trying to carry your tray of drinks through, you're going to have to slow down. Now in this instance, you are the electron and you're trying to get through the wire. And when your party mates are dancing, they're like the ions that are heating up. Suddenly they're getting in the way. They're vibrating, they're moving, and you as an electron are forced to slow down. And that's what's happening in the wire. So you should have, as your notes, 2 graphs, 2 sets of sentences explaining them. Now you can go on and do your questions. Please let me know if you have anything you're not sure of. I'm always here to help. But yeah, see you soon. Bye.